Today, we would like to introduce our luminous environment total analysis simulation, LETAS. Generally, luminous environment in a space refers to the brightness distribution on each surface of the space as a visible scene, but since humans act within a space, the light distribution inside the space is also important. Until now, the light distribution inside a space has not been given much importance because it cannot be seen by our eyes. However, as soon as people or fixtures are placed inside a space, the light distribution appears and affects people's behavior. Conversely, if the light distribution inside a space is known in advance, the effect of light on human behavior can be predicted, making it easier to consider the placement of people and fixtures. For this reason, in lighting design, it is important to anticipate the light distribution inside a space as well as the brightness distribution on each surface. As a tool for this, we propose the Luminous Environment Total Analysis Simulation, LETAS. Specifically, it is a comprehensive simulation of the luminous environment that combines the Brightness Comparison Index, BCI, which evaluates the brightness of the entire space, the vector scalar ratio plus, which shows the amount and direction of light and the intensity of the object's shadow inside the space, and the luminance distribution map on each surface of the space. The BCI and the vector scalar ratio plus are our original. First, the BCI is an index that compares the brightness of the entire space. It is positioned in the early stages of lighting design as a simple brightness index that is independent of viewpoint and viewing direction. The BCI is displayed by the size and color of a sphere, making it possible to compare the brightness of different spaces. In the case of a single room like this example, this is a guide to the brightness of the entire space. The larger the size of the sphere, the brighter it is, and the degree of brightness according to color is as shown in the color scale. Since the indirect illuminancy of each surface of the space corresponds to the amount of light in the space, the specific BCI value is calculated by taking the natural logarithm of the area-weighted average value of the indirect illuminance of each surface. Next, the vector scalar ratio plus is a simulation consisting of multiple light elements at each grid point inside a space. It is an application of the vectorscalar ratio, and shows the amount and direction of light, as well as the intensity of object's shadow. The vector scalar ratio is the magnitude of the illumination vector divided by the scalar luminance, and is an index used to evaluate modeling, that is, the three-dimensional effect caused by the object's shadow. In addition, scalar illuminance shows the amount of light, and the illumination vector shows direction of the light. In the vector scalar ratio plus, the color of the arrow at the calculation point shows the scalar illuminance, the direction of the arrow shows the direction of the illumination vector, and these eyes of the arrow shows the vector scalar ratio. This makes it possible to simultaneously show three elements: the amount of light, the direction of light, and the intensity of shadow. Here, we compared the luminous environment of the entire room under daylight using the LETAS. This is a comparison of the vernal equinox, summer solstice, and winter solstice when windows are installed on the south and west sides. Furthermore, a version of the LETAS that adds numerical displays such as power consumption and average luminance is called LETAS E. This allows designers to check not only the luminous environment at a certain time but also the power consumption at the same time, for example, when daylight and artificial light coexist. In the initial version, luminance distribution maps were displayed on all surfaces, but from this version, illuminance distribution maps are used only on floor surface. The living room with a vaulted ceiling has 2 windows facing the south, and the dining room with a low ceiling has 1 window facing the north. The living room is lit mainly by spotlights, while the dining room is lit mainly by downlights, each dimmed to maintain an average illumination level of 300 lux on the floor. Finally, a high-resolution version of the LETAS is called LETAS H. This is the luminous environment with daylight from a south-facing window at 10 o'clock on the vernal equinox under the CIE standard general sky. At first glance, this may seem like too much information, but since it is expected that we will be examining the 3D simulation space from various viewpoints in the future, the necessary lighting elements are emphasized depending on the viewpoint. For example, if the viewpoint is set at the center in the room and the viewing direction is horizontal when looking at the wall, the luminance distribution map is emphasized. Similarly, if the viewpoint is set at the center and the room and the viewing direction is directly below when looking at the floor, the illuminance distribution map is emphasized. The sphere showing the BCI is placed in the center of the room so that it is not affected by moving the viewpoint. The LETAS is usually an isometric projection, but the perspective version of LETAS H looks like this. Whatever the method of simulation, it is important to design the luminous environment using absolute values rather than relying solely on the senses in order to carry out objective lighting design. Especially in future lighting design, where the SDGs will be emphasized, it will be necessary to consider detailed, human-centered, luminous environment and optimize energy consumption. For this purpose, we believe that a comprehensive lighting design method using absolute values of various evaluation factors will be an effective approach. That's all. Thank you for your watching.